Today we talk about fuel cell types. At the end of these modules, you will be able to list and compare the main fuel cell types, describe the application of different fuel cell types depending on their operating conditions, and select the most suitable fuel cell type for a given application. Different types of fuel cell differ for materials that compose electrolyte and electrodes, and the type of reactions that occur. Given two material constraints and the electrochemistry, this also results in different operating temperature. Because of the dependence of the voltage to the operating temperature, we can see also that different fuel cell types show different range of voltage. We're gonna look now into more details for four types of fuel cells, four very common types of fuel cells. The first is proton exchange membrane, or PEM, sometimes also called a polymer electrolyte fuel cell, PEFC. The PEM fuel cell has a polymer electrolyte, and the reaction that occurs inside is with hydrogen and oxygen, such as the most common fuel cell that we looked at in the last module. Water is formed on the cathode side. One important characteristic of this fuel cell is that for the electrolyte to be conductive to hydrogen protons, water needs to be present at liquid state around the electrolyte at all the time. For this reason, if the fuel cell operates in atmospheric condition, the temperature needs to be lower than the water boiling point. This is why normally this fuel cell operates around 40 or up to 80 degrees C. Another important characteristic is that it's very sensitive to even small traces of carbon monoxide, which degrades the material very quickly. So the fuel needs to be pre-processed and clean. Thanks to the polymer electrolyte, this fuel cell is very light and compact. This, together with the low operating temperature, makes it perfect for transportation applications. There are many examples around the world of cars, buses, or trucks that use PEM fuel cell for the traction. One barrier yet is the need for hydrogen infrastructure and also the challenges that are related to hydrogen storage in the car. Another application is for generation of power at very, very small size to replace batteries. We are talking about power that is less than 1 watt, and fuel cell is a technology that can be extremely efficient for such a small power. So it has been suggested to use, instead of battery, fuel cell with the advantage of no need for electricity to recharge the battery, but they just need for storing the fuel. PEM fuel cell had found some application in this field, together with direct methanol fuel cell, which are fuel cells that can use directly liquid methanol as a fuel. Another type of fuel cell that we are going to look at is phosphoric acid fuel cell, PAFC. These are very similar to PEM. The same type of reaction happens inside, but the electrolyte is a different material. Water doesn't need to be at liquid state, and this fuel cell operates at a higher temperature, about 200 degrees C. So it is very suitable for also cogeneration application in case we need also some heat at a relatively high temperature. This was also the first fuel cell to be commercialized. And one advantage with respect to PEM is that it's tolerant to small traces of carbon monoxide. Molten carbonate fuel cells operate at much higher temperature. We are talking about 600 to 700 degrees C. One interesting aspect of this fuel cell is that the reaction that occur inside are quite different from PEM. If you see in this figure, the ion that is transported through the electrolyte is a carbonate ion. So a lot of CO2 needs to be present on the cathode side. So the reaction that happen on the cathode side are to combine oxygen and carbon dioxide to form this carbonate ion that can pass through to the anode side, where it reacts with hydrogen to form water and CO2. CO2 can then be recirculated on the cathode side. Of course, the air on the cathode side needs to be enriched with CO2 because the CO2 needed is much higher than what is present naturally in air. This suggests that MCFC could be used for temporary storage of CO2. Because they have high operating temperature, they can use a cheaper catalyst instead of platinum, that is used in PEM and PAFC. And also it can use different fuels other than hydrogen. Solid oxide fuel cells also are considered high temperature fuel cells. Operating temperature is even higher than MCFC. Their electrolyte is of a ceramic material. The reaction that occur inside are again between hydrogen and oxygen, but differently from PEM is the oxygen ion that is transported from the anode side to the cathode the cathode side to the anode side, where it reacts with hydrogen and forms water at the anode side. Because the electrolyte is ceramic, it is very fragile and it is very sensitive to thermal stress. So this type of fuel cell cannot tolerate sharp temperature variations. But because of the high operating temperature, it is very efficient. Nickel can be used as a catalyst instead of platinum, and different fuels can be used. We will look into it more in details. It is also suitable for cogeneration because a lot of heat is produced, or combined cycle, where the fuel cell can be treated as the heat source of the cycle. Solid oxide fuel cell can have a planar configuration where anode, electrolyte, and cathode are piled together, and then a single cell of area of around 10 to hundreds of square centimeter can generate less than 1 volt. Hundreds of thousands of fuel cells are then stacked together to reach the desired power. Configuration of planar SOFC can be divided in co-flow, in case the fuel and the air flow in the same direction, counterflow, in case fuel and air flow in 2 different directions, or cross-flow in case the directions are perpendicular. Another geometry of SOFC is tubular fuel cell. In this case, cathode, electrolyte, and anode form a microtube. Usually, as we saw in last module, not all the fuel is oxidized in the fuel cell. There is always about 20–30% of excess fuel that leaves the fuel cell. So mostly in fuel cells, especially in high temperature fuel cells, there is an area called post-combustor zone or off-gas burner where the excess fuel and the excess air meet. The excess fuel ignites spontaneously because of the high temperature, and so all the excess fuel is totally oxidized, and additional heat can be produced in the fuel cell stack. One last point that we will touch in this module is about reforming reaction. There are 2 reactions that can occur at high temperature above 500 degrees C, usually in presence of a catalyst. These reactions are used to convert methane into hydrogen. The first reaction is called steam methane reforming because methane reacts with steam to form hydrogen and CO. So this reaction requires high temperature, requires heat from an external source. A second reaction is called water gas shifting, where CO reacts with water to form hydrogen and CO2. And this reaction is exothermic, so it produces heat. Similar reactions happen also with other hydrocarbon that contains carbon and hydrogen. So, in fuel cell, where the operating temperature is higher than 500 degrees C, in presence of a catalyst and steam, this reaction can occur spontaneously. And this is why in MCFC and SOFC, methane can also be used as a fuel because it will be automatically converted in hydrogen, which then takes part in the reactions to produce current. This reaction can happen either outside the fuel cell in a separated reactor, and here we talk about external reformer, or the reformer can be integrated in the stack and take advantage of the heat produced by the fuel cell to sustain the reforming reaction, or in high temperature fuel cell, the reforming reaction can happen directly on the anode, as I just said, because of the high temperature and the presence of steam. Methane can be converted directly in the fuel cell to hydrogen. Of course, this case limits the amount of methane that can be converted because the size of the fuel cell is fixed. High temperature fuel cells such as MCFC and SOFC are very suitable for combined heat and power application because the exhaust gas is a very high temperature. So this makes those types of fuel cell very good, very promising for stationary application where both electricity and heat are needed. In conclusion, we have seen mainly 4 types of very common fuel cells, which differ from the application that are more suitable for the type of fuel that they use and the temperature they operate through. Reforming reactions can be used to convert methane or hydrocarbon into hydrogen for fuel cell, and the reformer can even be integrated into high temperature fuel cell. Thank you, and see you in the next